Hello and welcome back to part 3, which is the last part of the basic radar physics, math and geometry tasks in the slide deck of the introduction. Let's go to it. What are the takeaways so far? I hope that the audience right now, at this point in time, knows that radars cannot look around corners and are limited by the processing and intelligence, so to say. There they are not comparable with the human eye or the human brain, but are more limited on their field of view. I hope that everybody knows that we need an obstacle that reflects back to the radar sensor to actually see this obstacle. We cannot see what is not there, or we cannot see what is deflecting the radar energy. Radars can also not look behind obstruction, and as soon as an obstacle is detected, whatever is behind, there is a limit of probability to see this. With all this, it is on us, and in this case, in the project phase, it's important to select the correct technology, also in the numbers, that the maintainer and installer puts it in the right position and makes sure that it stays in the right position, so it's maintained. And when it's installed and running, that the operator knows how to operate and interpret this sensor data. In fact, in all of these different layers, it can be that failure is programmed into the organization because either one or multiple layers fail and need to be then fixed later on, which is always very difficult to then retrain. So let's go deeper into the field of view. And when we have success and when we have failure. First example, in blue, there is, maybe I can even, no, I cannot. In blue, there is the human eyesight operator field of view. In red, it is what the radar sees. Here we see that the person is invisible to the human eye field of view, but visible to the radar. Success. Now we have the same, maybe at night time. The view of the human eye, the operator, is limited, but still we have success and actually the enablement through the radar technology because it's not impacted by these conditions. The opposite is true in good conditions, especially when the operator can see because of elevated position behind obstacles and the radar is limited, for this example, by a berm, cannot look behind it. Here it makes completely sense by design, but it's important to keep always the field of view mismatch in the back of the head, especially for the situations where we look behind the truck, where we need again mirrors or CCTV cameras to then rely on this, and especially far away objects are then difficult to spot. And again, the radar technology can help in really finding obstacles, humans, other vehicles, whatever. Here it's again depicted as a human. It's just important to say that also what we call the information overflow is important to keep in mind, because here an operator needs to check the mirrors, check CCTV, a camera display, needs to check a radar display. So there's a lot of aid, but it's also opening the door for confusion. Finally, When do we fail? Even in good conditions, when there is still a field of view mismatch. I have a field of view gap. Either the installation was not done correctly planned, correctly executed, or not correctly maintained and controlled. Here the radar looks only downwards and is missing a person that is standing in front of the machine. Now everybody can say, if I'm driving the vehicle, this person would have been in the field of view already, or if I'm starting up the equipment and only start moving now, I will again see the person or the obstacle, but it's simply here as an example that this is actually the failure mode, which is quite likely to happen, that there is something appearing in front or behind the machine that I was expecting to be seen, but finally it ends up undiscovered because of a field of view mismatch. And the second case is also very likely. Here I am in nighttime conditions again. Maybe I have a person that is also not wearing a reflective vest and PPE. So on the one hand side, I'm limited by the visual reflections of this person, of light. And it is maybe also a person standing in an undesirable, making an undesirable gesture, making the radar cross-section small as possible. And also the radar has not enough reflective energy to see this target. It happened to me many times where, for example, somebody wants to test the capabilities of a radar at night time, and I'm saying it doesn't really make sense because night and day to the radar it doesn't make a difference. And then they put on in plastic mannequins instead of real humans. It's a fair thing, but it's always more difficult to detect plastic than it is with a human body. Anyway, I hope that now the picture is slightly coming together on how simple and how complex the topic is at the same time. So back to the basics. Radar cross-section. We know that the radar cannot see something that is too small and has not enough reflectiveness, or the size is too small. And we also know that the radar cross-section is not a constant value, but dependable on properties and orientation. So how can we make sure that an alarm is triggered when we need it, but still we want to keep the nuisance and also the false positives? That means I get an alarm, but it's not really necessary, down to the minimum. Because for an effective alarm, it should only alarm me when it's necessary. And I lose trust into a system that is giving me too often a false alarm. So maybe I also do not have the resources to always place volunteers in front of the machine to do radar tests. The question is, how can I succeed in confirming the effectiveness of our system, of the radar system, in our conditions, in our mind-specific environment? And here a solution is, again, quite simple, to use a radar reflector. It's a very specific hardware with a very simple work principle that you maybe know from cat eyes in the dark, or the modern reflectors as we have them on bicycles or motorcycles or boats. So you can even buy this basically in naval shops, and you can also wet them together as you have the material. They are either stacked up like this or look like that. You can get them in aluminum or in some sort of plastic. Again, keep in mind this has an effect, and different shapes and sizes. You can always either compare, if it's given, the size and comparable size in a datasheet, or can make the calculation, which I will explain somewhere else in another slide deck. For now, we just need some rule of thumb values again and some basic information, which is the typical RCS values for a human 1 square meter and for pickup roughly 200. Keep in mind that you do not want to make the situation worse, the safety and count of injuries and lost time higher by actually trying to introduce a technology. So keep safety always in mind when concluding tests and trainings. But you also want to have them comparable. Maybe today you make, if you take, for example, vehicles as targets, maybe today you take a small car, tomorrow you take a bigger sized truck or pickup truck, and the day after you take a bus. Of course, the values would not be comparable, and what you train team number 1 can be different to team number 2. So it really makes sense to indicate the radar cross-section that you want to test for, get a radar reflector or multiple ones, and keep them in the training and testing procedure. It is also fair to tag specific infrastructure or even vehicles with reflectors when you are wanting to be on outside the box. Let's rethink this. When it comes to our human eyes, it's also possible to tag equipment that you do not want to lose track of. This is what we do with the whips or with specific lights, to just keep track of equipment at all times. It would also be completely fair to equip a radar reflector to mine vehicles, and it is also fair to tag infrastructure with reflectors that otherwise you have a level of uncertainty to see them from all directions. So we remember that intelligence is the measurement of identifying your own reflection, this mirror example. And here again, it's also questions of thinking outside the box and to future-proven your design and your layout, how you conduct the technology into your existing infrastructure. You can make your infrastructure more radar-proof and then need to worry less about the radar itself. It's like a two-side approach. Another topic that we need to cover to complete the basics is that a radar can basically not see what is very, very close to it. You can compare it with some person holding the hand in front of your eyes. At some point you would not know if your eyesight is like stopped working or if you're just blocked from a third party. Same happens with the radars. If you block them, for example putting your palm of the hand right in front of the sensor, most radars will have this minimum distance of acceptance and go to an unsupported operation, shut off and don't react anymore if the very close front of the radar, so the very close view, is completely or by high percentage blocked. This minimum distance, when they go in this special mode, is unique and technology dependent per radar. So this minimum distance, there is also not a fixed value where you can say it would be 20 centimeters, 30, 50, or up to 1 meter. It's dependent on radars. This is again a near miss behavior that I have seen multiple times, what I call the radar detection bias. You need to understand this distance because it's also important for your knowledge when does the radar become blind to me in the very close proximity. If I want to trigger a radar behavior in functionality tests and maintenance, I need to know when this shut off offset is actually happening, and also if I need to trigger a response in an emergency situation that I really want to be visible to the machine, to the radar, it's important to maybe take a step back actually than getting closer to the radar. That's maybe not the first the first logical thing to do, but it is, once you understand how radars work, the effective response. So let's identify the most common near misses. It's always the out of view context. I can be out of view because I am too close. I can be out of view because I have a gesture that brings me out of view of the radars. And I can be out of view intentional because I move around the equipment like a ninja in full purpose not to be seen. All three modes may it be because, I don't know, I conduct work that requires a certain posture, or I just lost consciousness. May it be because I don't know how this radar works, so I'm not aware of the danger. Or may it be because I'm actually trying to not intervene or have some hidden agenda personally. All these can lead to the failure of the system. So let's wrap it up, come to an end. Is the radar technology really useful for my use case? To answer this question, everybody must ask the same questions first and find the correct answer and document. I need to know what the radar can see, what it cannot see, the entire topic of the last slide decks. I need to know that mining radars do not have this 360-degree field of view, but are specific sensors with an opening angle horizontally in azimuth and vertically in elevation. I can always help myself with the human eyesight, but I must be aware that still the radar sees the world in a different wavelength and with a slightly different logic approach. I need to know which cases occur in my operation, when do I want to have radar feedback, and when do I not want to have radar feedback. So I need to distinguish the wanted and unwanted alarm events. Finally, everybody on each single task and position, everybody must agree and participate in the use case. We must be sure if we want to have one or multiple radars, which is again different on the piece of equipment and what I want to achieve. Depending on that, the field of view and the technology, in-depth technology used in the radars. And my most challenging conditions, my most challenging to detect targets, and most of the time it will always be the human detection, which is the most challenging because of multiple reasons. To make it comparable, I need to come with the right technology, as discussed prior, the radar reflectors. To end it, I prepared questions, as you are by now well aware of. Remember, 1 of 3 we had in the part 1, so now there are only 2 more to go. Can answer these questions. They should be quite simple now, as you became experts. You can stop the video here and answer them for yourself. If there are questions, the comments are always possible to use for solving. With this, I thank you for your participation. I congratulate you for being now a radar expert, having the most basic knowledge, not only what this technology can do, but also some understanding of what it cannot do. I hope you know how it can help you. Now you know how it can bring you even into dangers and what is your correct response. We will move on with how to really find out and work with this technology, and I hopefully see you again there. With this, thank you very much for your curiosity and goodbye. If questions arise, you know how to respond and who to connect with as your responsible training personnel.